All right, let's jump right in. Today, we're unpacking the mechanical journey of TCP data transfers. We're going to go from the theoretical interfaces that actually allow machines to talk to each other all the way down to solving complex gate exam questions using operational mathematics. If you've ever wondered how your browser establishes a rock-solid connection to a server without dropping a single byte, you are in exactly the right place. Here is our roadmap for this explainer. We're hitting the network socket interface, TCP connection establishment, connection-oriented demultiplexing, TCP buffers and variables, and finally, we'll look at some gate exam applications. Let's get to it. Section 1, the network socket interface. So I want you to literally visualize this as a door. A network socket is basically the interface of a network process. Think of a process as, say, your web browser talking to a web server. This socket, it's a specific data structure acting as one endpoint in a two-way communication link. Data simply cannot leave or enter a process without passing through this exact doorway, period. If two processes on different machines want to communicate, they absolutely have to do so via a pair of these sockets. Now, at the transport layer, you've generally got two types of these doors. A UDP datagram socket just kind of fires data out into the void, like dropping an untracked letter in the mail. But today, we're strictly focusing on the TCP stream socket, the sock_stream. Unlike UDP, TCP demands a highly organized, established connection before any actual data can flow. It is a logical, point-to-point, full duplex tunnel. Moving into Section 2, the TCP connection establishment phase. So let's look at the famous three-way handshake. How exactly does this build that logical tunnel before a single byte of application data is transferred? Well, step 1, the client knocks on the server's door by sending a SYN, or synchronize, segment. Step 2, the server acknowledges that knock and agrees to connect by firing back a SYN ACK, an acknowledgement. And finally, step 3, the client confirms the server's agreement with an ACK, an acknowledgement. Boom, connection established. Now, this is where it gets really interesting. Track the exact state transitions happening under the hood here. Look over at the server side on the right. Notice how the server just passively waits in a listen state. It only jumps to the SYN RCVD or SYN receive state when it gets pinged by that initial SYN from the client. It just sits in that waiting room until the client's final ACK arrives. Only then does it transition into the fully established state. You know, memorizing this specific sequence is absolutely critical for nailing transport layer logic. Which brings us to Section 3, connection-oriented demultiplexing. Okay, the absolutely crucial point here is the four-tuple. This is exactly how connection-oriented demultiplexing works. A server doesn't just look at where the data is going, it looks at exactly where it came from. Think of it like a bouncer at a highly secure building. They don't just need to know who you're visiting, your destination IP and port. They need to know exactly who you are and where you came from, the source IP and port. By checking these 4 specific variables, a massive web server can perfectly sort incoming traffic, handling thousands of clients concurrently without ever mixing up their streams. It's brilliant. And this perfectly illustrates the real trick servers use to manage ports. A server uses one general welcome socket on a specific port, let's call it port B, just to listen for new SYN requests. When a request comes in, it doesn't tie up that welcome socket, no way. Instead, the server process forks, literally cloning and spawning a brand new child process with a dedicated connection socket just for that single client's actual data transfer. Meanwhile, the welcome socket goes right back to listening for the next client. It's just an incredibly elegant solution for network scaling. All right, Section 4, TCP buffers and variables. Now, to avoid cognitive overload here, we've got to cleanly separate the sender's state logic from the receiver's state logic. Inside these dedicated sockets are send and receive buffers, and they track everything using very specific variables. The sender, which is pushing data out, tracks the last byte written by the application, the last byte sent over the network, and the last byte acked by the receiver. On the flip side, the receiver, which is waiting for data, tracks the last byte read by its application, the next byte expected from the network, and the last byte RCV'd. These buffers and their mathematical trackers, that's the absolute secret sauce of TCP flow control. Let's actually look at how these variables initialize during the handshake. Every single connection starts with an initial sequence number, or ISN. So if a client randomly chooses an ISN of X, say 500, then the next byte expected by the receiver mathematically becomes X plus 1, or 501.
The handshake itself consumes exactly one sequence number, even though there's zero application payload sent. Treat this like a golden rule. This X+1 operational formula guarantees both sides are perfectly synchronized before the real data transfer even starts.
Let's put this into practice. Section 5, Gate Exam Relevance.
Okay, let's test this logic with a classic multiple choice question. We have a TCP client calling connect, sending a SYN. The server responds with a SYN-ACK. The question asks, as per the TCP connection state diagram, in which state does the server-side TCP wait for the final ACK segment from the client? Is it SYN sent, SYN received, listen, or established? Well, if you recall our visualization of the state machine from earlier, this is testing exactly what happens right after the server replies to the initial ping. And there it is. The correct answer is B. The server waits in the SYN_received state. Remember, it left the listen state when that first SYN arrived, and it actually can't enter the established state until that final ACK comes through. This just goes to show that having a mental map of the state machine is your absolute cheat code for these kinds of problems. All right, let's tackle a slightly harder one, a multiple select question, or MSQ, testing our grasp of those buffer variables and sequence math. And since it's multiple select, keep in mind there could be more than one right answer here. Client P connects to server Q. P's initial sequence number is NP. Q's acknowledgement number in the reply is NQ. So which statements are correct? Is NP always 0? Is NP chosen randomly? Is NQ equal to NP? Or is NQ equal to NP plus 1? By looking closely at this timeline, we can easily track the operational logic. First off, the client absolutely does not start at 0. It chooses a random initial sequence number, N_P, mostly for security reasons. So statement B is true, meaning statement A is out. Now, what exactly does the server acknowledge? Well, think back to our golden rule from a few minutes ago. The handshake consumes exactly one sequence number. Because of that, the operational logic guarantees the server's acknowledgement, and Q strictly increments that base value by exactly 1. The server is literally saying to the client, hey, I received your SYN at NP, so my next byte expected is NP plus 1. So statement D is also true, making the correct answers for this gate question B and D. Once you truly master these underlying operational formulas, this math literally becomes an unlocked cheat code for the exam. So by simply starting with the concept of a doorway, we've successfully navigated all the way through multiplexing, operational buffers, and some pretty complex exam formulas. We saw how a single listening socket forks into dedicated connection sockets, and how these mathematical variables, like sequence and acknowledgement numbers, keep the entire system perfectly synchronized, byte by byte. Hopefully, this explainer has totally transformed how you view data transfers, and maybe left you a bit curious about the invisible state machines powering your every click. Next time you connect to a server, ask yourself, are those welcome sockets in a listen state waiting just for you? Or are they already busy forking child processes to handle your data? Keep exploring, keep questioning, and we'll see you in the next explainer.